class of distributions. Namely, this set f of x theta is a polynomial family if for any moment r, we compute the expected value of x from fx theta of x to the r, and that we're going to define as mr of theta. And we want that this is a polynomial in the parameters theta that we want to learn. So this is just some abstraction of what was the main idea going into Pearson's 6 moment test, which is this observation that any moment that you take of a mixture of Gaussians itself is analytically some polynomial in the underlying parameters. And we wrote out explicitly what these polynomials were, at least for r equals 1, r equals 2, r equals 3, and they get much more complicated. But now what we're going to do is we're going to work with any family whose moments are themselves polynomials in the parameters. So this is where the tools from algebraic geometry are going to start being useful, is that when you think about knowing what the moments of a distribution are, let's say exactly, that itself is some polynomial constraint on the underlying parameters. And we proved last time in the epsilon equals 0 case was just how far do we have to go down in the system of polynomial equations until knowing the exact right-hand side perfectly constrains the underlying parameters. So that's the exact question. But some of the tools from algebraic geometry will also be useful in addressing things like what happens if you have a noisy estimate of this right-hand side, and black box why are systems of polynomial equations at least somewhat stable when they're over a finite number of variables and have finite degree. So that's the roadmap for today, is to try and build on this intuition. So are there any questions about this? This will be our general framework. Now, it won't quite be enough that a family is a polynomial family, but there's a rather tame condition on a polynomial family that we'll also have to use, which just ensures that if we knew all of the moments of a distribution, that at least that would pin down what the underlying parameters are. So what we really care about is why do a finite number of moments suffice? And there'll be a rather tame condition which will tell us something like, for general classes of distributions, at least if we had all of the moments right, then we would perfectly know the parameters. Actually, first let me give you some examples of that fit into this definition. So the first one, we already talked about it, is a Gaussian. So the same way that the moments of the Gaussian are polynomials, the underlying parameters, you can also work with mixtures of Gaussians. Because when you compute the analytic moment, then all you're going to do is you're going to average based on the mixing weight, so you just get more variables thrown in. So that's a nice thing about this definition, is that as long as you're building up some family of distributions from pieces which are themselves fit into this polynomial family, you'll still get a polynomial family. We start with Gaussians, they're in the polynomial family, and we move to mixtures of Gaussians, and we still have something in the polynomial family. But there are a few other examples that are worth taking note of. So if you take a Poisson distribution, then it's easy to see that Poisson is parameterized by just one parameter lambda, and that parameter itself defines all of the moments, which are polynomials in lambda. So they're just 1, lambda, lambda squared, and so on. That also allows us to work with mixtures of Poissons too. And you can even do things like, there's the gamma distribution. And the same way you can work with mixtures of gamma distributions. So what we're going to prove today is that for all of these examples, that a finite number of moments suffice to uniquely determine what their underlying parameters are. Now the catch is that the bounds are going to be ineffective, because all we're going to know is that if you give me any example of a polynomial family, be it a Gaussian or a mixture of 3 Gaussians, or a Poisson or a mixture of 4 Poissons, whatever fixed polynomial family you give me, there's some finite bound, which we won't know what that is, but it can't be infinite. That'll uniquely determine what the underlying distribution is. So that's the outline. Let me tell you the last tame condition we're going to need on the family distributions to make this happen. So I'll just assert this fact, but the crucial fact that we're going to use is that there are quite nice conditions under which, if we had all of the moments of a distribution, if 2 different settings of the parameters theta and theta hat created distributions f of x theta and f of x theta hat, which have all of the same moments, then there are nice conditions on what this family is that ensure that actually their density functions have to be the same. So let me state what that is. But it has to do with the moment generating function, which I'll just define. So if the moment generating function So you can define the moment generating function this way. We're not really going to use it, but this is a condition we formally will need. If you take the expectation of e to the t x, where x comes from your underlying distribution, then the way that you can write this out is you can write it as sum over r of the expectation, x sampled from f of x theta, of x to the r, times t to the r over r factorial. So in this way, if you take this random variable, for any fixed value of t, you can compute what this expectation is. And you can think about t as a formal variable then, and then it has some expression, some infinite sum that expresses it. And when you expand it out, each of the coefficients in this t to the r over r factorial will just be the moment. So the moment generating function is a way to capture the properties, the moments of some underlying distribution. It's a great way sometimes for some of these distributions, you can prove that they're in the polynomial family either by direct computation for something like a Gaussian or a mixture of Gaussians and doing some integration by parts and convincing yourself you always end up with a polynomial. Or for other parts of these distributions, what you can do is you can just write out explicitly what the moment generating function is and then expand that to figure out what the underlying moments are. And that's another convenient way to think about why a family fits into this polynomial family definition. But what I want to say is that if this moment generating function converges in neighborhood of 0, then the sort of basic fact that we're going to use is that if 2 settings of the parameters match for all r, so all of their rth moments are the same, that'll imply that f of x theta is the same thing as f of x theta hat. So it allows us to say, a priori you could match on all of your finite moments, but not still be the same density function. One way of doing that is to sort of change what the density function is on some measure 0 set, or do some other things that are just not nice for this distribution, but under rather tame conditions, namely that this moment generating function converges in the neighborhood of 0, matching in all of your moments is sufficient to guarantee that you've learned all that you could possibly learn about your distribution, because whatever setting of parameters you have, you produce exactly the same density function. So this is the same way that for a mixture of 2 Gaussians, we can't hope to learn which one is component 1 and which one's component 2. But what we showed is actually that when you agree on the first 6 moments, so not all moments, but on the first 6 moments, we showed that that implies you're actually the same density function, and you've done all you can do. Now, the other direction of this is also, obvious that if f of x theta equals f of x theta hat, then of course you match on all of your moments. So this is just a tame condition about some convergence properties of the moment generating function, which in turn will allow us to think about not the original density function, but just systems of polynomial equations. And what we really care about is when they start becoming redundant. So maybe matching on the first 100 moments is enough to guarantee that actually you match on the 101st for free too, because you're not getting algebraically independent equations as you continue to grow. So that's explicitly the property we're going to use, is actually properties from algebraic geometry that when you define increasing sets of ideals, which I'll define in a minute, that you don't keep increasing forever. And that'll allow us to sort of weaken this condition. Instead of saying that you match on all moments, you're just going to match on some finite number of moments. So that's the plan of action. All right, so I need to introduce some general definitions from algebraic geometry so that we can get this plan off the ground. But we're going to use these tools to reason about the moments and show that a finite number of moments suffice. So the crucial definition that we're going to use, at least from algebraic geometry, is the notion of an ideal. And I won't foreshadow exactly how we use this. It's very simple, but I think it would just be confusing at this point. But the idea is we're given some ring R. You can think about this as either being all the real values, or you could think about it as, for example, being a ring of polynomials. And some formal variable x. Well then, the crucial idea is that we can define an ideal which will be generated by some elements in this ring. And we're going to denote this by I of bracket G1, G2, all the way up to Gn. And what it is it's just the set of all things that you can get by multiplying these generators by other elements in the ring. So you can think about this ring, just for simplicity, as being univariate polynomials with coefficients which are reals. That'll be one of the simplest settings where this is not really a vacuous definition. I'll show you some examples in a minute, but the basic idea is that we're going to start off in that case with some univariate polynomials that belong to the ring. And what we're going to do is we're going to consider all univariate polynomials, which we can then create by taking combinations of the GIs weighted by some ring elements themselves. So let me give you an example to make this concrete. Are there any questions about the definition, though? So for example, let's choose this ring to be all bivariate polynomials on the variables x and y. So these are just polynomials in these formal variables x and y, whose coefficients are reals. So this is one example of a ring that we would care about. It's just rings over two variables. And so, just to state this precisely, it's the set of all polynomials over x and y with real coefficients. Well, let's consider the ideal generated by x squared y and y squared x. So again, just appealing to this definition, I'm going to choose these generators, G1 and G2. They both have to belong to the ring, so I can choose, for example, x squared y. That's certainly in this ring that I'm interested in. And I could choose y squared x. Now, what should be the set of bivariate polynomials that I would generate from these two base elements? What ideal would I get?
Could you repeat the question?
Yes. This is the definition of an ideal. It's a bit abstract. You know, we're not in an algebraic geometry course, but we're going to use this definition. So the first thing I want to do is I want to make sure you understand how to parse this definition. Let's apply it in this simple case where the underlying ring is the set of all bivariate polynomials. And what I want to know is just if I define the ideal generated by x squared y and y squared x, what set of bivariate polynomials do I get? What's a description of the ideal?
It's like xy times x plus y plus some other like polynomial.
So let me ask it this way. So one way of doing it is, the first question is, what sorts of monomials can I get out of this? And then I can take any linear combination of those monomials I want. That'll actually be my set of ideals. So what types of monomials can I get? Like, what sorts of restrictions on AI and BI should be true here? So can I get x1, x times y? No, right? Was there an answer?
So AI plus BI is greater or equal to 3?
Yeah, well, no, not quite, because they, see, I don't want 0, 3. So as long as you exclude that case, then it's fine. But,
well, you also need to exclude like 0, 4.
Right. So let me, so someone give me a different condition. Yeah, that's true. I need to exclude all those things. Someone give me a different condition on the AIs. And
They have to be at least 1.
yeah, but can I get 1, 1?
And they
No.
have to add at least 3.
Yeah. So let me just phrase it this way. So AI is at least 2, and BI is at least 1, or AI is at least 1, and BI is at least 2.
So you need coefficients.
Yes. Or these CIs are reals. And then this is the ideal we get. And we're going to come back to this example again and again, because actually this ring is going to be the source of the ineffectiveness of the bounds that we're going to prove. So we're going to use this example again and again. But does everyone understand the definition of an ideal and how to think about it as being generated by a set of elements? Now let's actually, I'm going to tell you an important property of ideals that's studied in ring theory and algebraic geometry. And we're really going to care about mapping that property to our problem about polynomial constraints using the method of moments. So these are the last definitions and facts we're going to use until we start applying things. But so a Noetherian ring, which will prove that many important rings that we care about, ones that come from the method of moments, have this property. But the property of these rings, a Noetherian ring R is a ring such that any sequence of ideals I1 is contained in I2, is contained in I3, and so on. There is some n such that in equals in plus 1 equals in plus 2, and so on. So we'll be interested in rings that have this property, that you can't keep adding to your ideal in a non-trivial way. You can't have that I2 is strictly larger than I1 and I3 is strictly larger than I2, and so on forever. There'll have to be in any chain of ideals there has to be some finite n, which after that point, the ideals stop growing. So the way that this is going to map back onto the method of moments is that we want to say that each time we add a new constraint on the moments are equal by looking at larger and larger values of r, we want to say that at some point these things become redundant and that we're not actually adding new constraints. So that's the basic idea about how we're going to map this notion of a Noetherian ring to why the method of moments will always work in these polynomial families for some finite moment. The same way that we proved that for mixtures of two Gaussians, the answer is 6 moments. We're going to prove it through the notion of a Noetherian ring. So are there any other questions? This is one of the more abstract lectures we're going to do. So stop me anytime. Make sense? Should I give you guys a minute to digest these definitions and then complain if you have questions?
I have a quick question.
Goes fast.
So, on the definition of an ideal,
Yeah.
the top definition goes through from 1 to n, but the bottom one also goes through 1 to n, but there's only 2 terms.
What do you mean?
That's different.
These are different, so let me put
Sorry.
it as m. So if you think about it, like, the way to think about it is I can certainly generate any x to the ai, y to the bi of this form with these constraints on ai and bi. And then what I can do is any finite combination of those, I can scale them by constants, and I can add them up however I want. So really the way to think about this is what's important is really what are the types of monomials that you can generate in this ideal, and then you're allowed any linear combinations of those monomials. So these are the types of monomials you can generate, and then you can add up any finite number you want. So the way to think about this is, why can I generate any such candidate? You give me an example of such a thing that meets these constraints. I'll generate each monomial in the ideal, and then I'll add them up with non-negative combinations. Any other questions about these definitions? Yep.
Does it have to be non-negative?
Sorry, any real combinations, yep. Any other questions about this definition?
Can you give me the formal definition of the ring?
So let's, we're only going to be working with rings of polynomials. So one thing you can think about is, if you look at the set of univariate polynomials with real coefficients, then what I can do is I can multiply two things, I can add them, and I still get something in that ring. Because when I add two univariate polynomials with real coefficients, I'm going to get a univariate polynomial with real coefficients. Same thing is true when I multiply them.
Any constraints on the coefficients?
No, so they have to come from some base field here. We're always going to be working over polynomials with real coefficients. So you can just think about this as a general definition that's a placeholder for univariate, bivariate, and so on polynomials. That's all we'll use it for. I could give you the definition, but then I think this will be swamped. So if you want to think about it just as polynomials with real coefficients, that's fine. Yep.
Maybe just as a sanity check, but is the ring of polynomials Noetherian?
Yes, so that's the next point that I'm going to get to. So we're going to use, so let me actually start with an even more basic thing. Let's say there's no variables. Is the set of reals Noetherian? So let's use this definition before we get to Ariel's question. So the simple thing is that if I choose the ring to be just the reals, so now I have no polynomials because there's no formal variable x. All I'm doing is just looking at the real values. And what I want to do, I want to say that this ring is actually Noetherian. So the way to think about this is that, imagine I have some ideal I, which is generated by G1, G1, G2 up to Gn. It's the set of all real numbers that I can obtain like this. So I claim there's actually only one of two options for what this ideal generated by these values is. So can anyone finish the proof? Yeah.
So either the G1 to Gn are just zeros, and in this case you generate only a zero,
Yeah.
or there's at least one non-zero number that you generate R.
Yes, exactly, right? There's two cases here. All the GIs are zero, then this ideal is just the zero element, else this ideal is the entire ring. Right? So pretty basic example of a Noetherian ring. I mean, it's good to have an example of it, otherwise it wouldn't be such a great definition. The important thing is actually that from rings that you can reason about very easily with a one-line proof, you can actually build up other rings that are also Noetherian. So the crucial thing that we're going to be using is the last tool for the time being before we get some applications, is what's called Hilbert's basis theorem. See, because the next question to ask after we know one ring that's Noetherian is we should ask whether R of x is Noetherian, whether the set of all univariate polynomials with real coefficients is itself also has this property that we want. Now you could prove that directly, the proof would get a little bit longer, and then maybe you'd want to prove it for R of x comma y, and that would get longer even still. But actually, there's a way to build up from a Noetherian ring another Noetherian ring, which is more complicated, which is just the statement that if any ring R, so this could be the reals, or it could be R of x, so univariate real coefficient polynomials. So if R is Noetherian, then R of x is 2. So here x is a new formal variable. So this is great. From the things we know, we can build up plenty of other examples. And now we're actually ready. So does the statement make sense? Are there any questions about this yet?
So can you say again what is R of x?
Yes, so what you would do is, so in the case, let's try out some examples, right? So we know when we choose this ring, it's Noetherian. Now, one other thing that we can do is we can then look at let me call this, ring 1. Well, we can look at ring 2 is R of x. These are univariate polynomials with real coefficients. We know this is Noetherian. Now what I can do is I can do something more interesting, because I can look at R of 3 is R2 of y, where y is a new formal variable. And what I'm really getting when I plug this in is R of x1. See, this is the ring of polynomials with variables y. And its coefficients are themselves univariate polynomials, which are polynomials in x. So what I get out at the end of the day are bivariate polynomials in x and y, because the coefficients in this ring R2 come from this ring over polynomials. So I can build this up and go to x, y, z, and so on. So each time I'm really just, in the setting we'll be interested in, we're just looking at polynomials over some variables with real coefficients. But the way that we're formally using this Hilbert's basis theorem is that we're sequentially applying it to a ring over some new formal variable, where the coefficients in that ring came from the old one. So polynomials in y, whose coefficients are themselves polynomials in x. And when you multiply that out, you get some polynomial in x and y. So these are the bivariate polynomials with, again, real coefficients. And again, we know it's Noetherian. Are there any other questions about this? We can use it now. So let's prove a finite number of moments suffice. So we're going to consider any polynomial family. And we need this other tame condition in addition, which you shouldn't really worry about. It's just some sanity check that if you had all of the moments, then you really do agree as a distribution. So we need this polynomial family constraint. We need this really tame condition on distributions. But then there's some finite n such that the following condition holds. MR of theta equals MR of theta hat for all r from 1 to n, if and only if f of x theta equals f of x theta hat. So this, just to put this in comparison, right? Remember that we had this tame condition, which was, not just satisfied by polynomial families, but it was really satisfied by, non-pathological things. And we had this condition that if you match in all moments from r from 1 to infinity, for all finite r, then actually your distributions match. But here we're substantially weakening this, because we're saying you only need to go out to some finite n. It's the same way that we talked about mixtures of two Gaussians, n was 6. Here we're going to prove that it's actually a general property that's just due to the fact that ideals over these rings that we care about cannot keep growing forever. So it'll actually be a very short proof once we assemble all these details. Let's prove it over here. There's only one trick in this proof. It's really short.
So Anchor,
Yep.
So the theorem statement is if the moment generating function converges in that neighborhood, then there is a finite, we only need finite number of
Yes.
moments.
If you have some family distributions that satisfies this polynomial family condition, so all of its moments are polynomials, the underlying parameters, and if it satisfies this really weak condition, this tame thing that the moment generating function converges some neighborhood of 0, then we're actually going to get this consequence that, obviously if you match as a distribution, all of your moments match, certainly the first n, but we're going to get a converse to this too, that actually if you match on your first n, then you have to be the same distribution. The catch is, I can't tell you what n is. but it's finite. So let's prove that. Very short proof. I'm going to define, this is the one trick. I'm going to look at some polynomial, QR, which will be a polynomial in the parameters in theta and the parameters in theta hat. All it will be is you take the polynomial of theta. So if the parameters were theta, what would the rth moment be? That itself is some polynomial in the underlying parameters. And I'm going to subtract mr of theta hat. So if I started off with k variables, I'm just going to 2k variables. That's the one trick. Now what I can do is I can define a sequence of ideals. I'm going to let I1 be generated by Q1. I'm going to let I2 be generated by Q1 and Q2. Similarly, for I3, it'll be generated by Q1, Q2, and Q3. So in this way that I've constructed it, it's obvious that the ideals are non-decreasing. They can only get larger because I'm just using more things in their set of generators. That's it, right? But now what we have is that these are all members of the ring of polynomials over the variables in theta and theta hat. They're formal polynomials whose coefficients are reals and whose variables can come from either of these two vectors, theta and theta hat. But we know by Hilbert's basis theorem, just by applying it for the ring R, then R of theta 1, then R of theta 2, and so on, and then including theta hat 1, and so on, we know that this is Noetherian. Hilbert's basis theorem gives us a way to manufacture a Noetherian ring from a Noetherian ring, and we just keep adding the formal variables until we're done. So this is Noetherian, which is great, right? Because it means that there is some n, so that in equals in plus 1 equals in plus 2, and so on. So the sequence of ideals cannot be strictly increasing forever. But what this really means, if you think about in plus 1, you're adding, in was generated by q1, q2, all the way up to qn. And in plus 1 was generated by q1, q2, all the way up to qn, and then qn plus 1. The only way that adding qn plus 1 does not increase the size of the ideal strictly is if qn plus 1 itself could be expressed in the old ideal. So what this means as a consequence of all of this is that for any n plus j, we can write q n plus j of theta hat is itself in the ideal in plus j equals in. All this together implies that we can express qn plus j of theta hat using the earlier things, the earlier generators. So these are just some polynomials in the ring, R of theta hat. So these explicitly play the role in the ideal of the R's, the little r sub i's. Those are exactly what you would get for these p sub i's. These are just elements of this underlying ring. And the only way that this ring, this ideal, has not increased is if the thing that we just added to it could have been expressed another way. So if it's in IN plus J, it's a generator, so it's certainly in that set. It's also in IN because those two ideals are the same. So let's just explicitly write out what that representation is. These are the generators for the nth ideal, and these are just elements, arbitrary elements of the ring. But now I claim we're actually in business, right? Anyone see why we're in business?
The first QI are all zero, then all zero.
Yeah, exactly, right? So think about what it means to match on your 1 through n moments. Well, that means these two things are equal, which means QR of theta, theta hat is 0. And then this entire expression is 0, so it implies that Qn plus j is 0. So the fact that these ideals don't keep increasing means that you can't have any surprises after some point. You're not adding algebraically new members to your family. And that once you match on the first 1 through n moments, it actually implies by this expression that you match on the n plus jth moment for any j. These linear coefficients may change. After all, they depend on I and j, but that doesn't change the fact that you're adding up zeros. Right? So that's the proof then. Let me just finish this up. Barely had enough room, right? So that's the end of it, is just writing out explicitly what Noetherian means, just using it on this simple ring of polynomials in theta and theta hat. What we're getting is just a bound that, at some n, you have to stop growing. And that means that when you match on the first n moments, you just use this expression, then you match on all of your moments. And then you use this tame condition that matching on all of your moments implies you're the same distribution under this condition on the moment generating function. So that's the end of the proof. Right? So are there any questions about this proof? There's a bit to digest, so let me give you a minute to think about it and object.
So Ankur, how does the last implication work? Like
this implication.
Yeah.
Yeah.
That last one.
That follows because I've assumed that the family always has a moment generating function that converges in the neighborhood of 0.
Okay.
And that's explicitly this implication. That when you have that property, a basic fact from probability is that matching on all of your moments implies the density functions are the same under this tame condition. So, this part of the implication, we use this Noetherian property, and this implication, all we did was we used this tame property about nice distributions. So the Noetherian property just allowed us to bootstrap, saying you match on all moments down to some finite number.
Do you have counter example for non-polynomial gathering? Because I'm very curious.
I don't know of any. That's a good question. I mean, one thing I will show you is, the question you should be wondering, or maybe I've sort of answered it already, is what is n?
Yeah.
So, even then you could ask whether n could depend on just what the underlying ring is. So if you took this argument and you applied it to the mixture of two Gaussians case, theta is a vector of 5 parameters, theta hat is a vector of 5 parameters. So you have a ring over just 10 variables. And the question is, can n, what this magical n is, where you stop growing, can that be expressed just as a function of the underlying ring you're working on? And the answer to that is no, right? So this is a provably ineffective bound, because the way that this is actually proven is the Hilbert basis theorem, for example, is you assume that there is infinite increasing thing, and then you'd reduce that to a contradiction on the underlying ring you're using to generate it, and you'd create some infinite increasing thing. So if you actually try and work out the ring over just R of x, so univariate polynomials, the way that you would try and prove that it's Noetherian, you would actually naturally come to many of Hilbert's ideas in that proof. But it's a proof by contradiction that you assume there is such an infinite increasing, strictly increasing chain, and you make that imply that there is one for the underlying ring too that's used to generate it. But the bigger issue is that even this simple example that I gave you of bivariate polynomials is already going to fail. That if I just look at the ring R of xy, then there will be a way that for any fixed n, I can create a sequence of chains of ideals that are strictly increasing up to n. So you cannot give me your finite bound before I tell you what the ideals are, is the issue. So let's see that. So for any n, there's a sequence of ideals actually in just this bivariate set of polynomials, which you're going to get, for any fixed integer n, you give me 100,000. There's a way to generate a sequence of ideals that is strictly increasing up to that point. So you cannot look at the ring and tell me the finite bound without knowing how I've constructed my example. So let me give you the simple example, very simple example. I guess let me call it GR in the nomenclature we've used so far. So what we're going to do is we're going to define GR to be this monomial, x to the n minus r and times y to the r. And what we're going to do is, if we think about, I1 is all things generated by G1. So x to the n minus 1, times y. And I2 is generated by G1, G2, and so on. Geometrically, what's going on here is that I can think about all of the monomials I can construct. And each of these monomials I can plot it on the grid based on what its coefficient is. So this would be y0, y1, y squared, y cubed, y to the fourth. This would be x